Cool. Is everyone well caffeinated and roughly awake for 4 o'clock in the afternoon? Yeah. I missed a coffee, so there's going to be some long, awkward pauses in here. Please give me some slack. Anyway, imagine this. You roll out of bed Monday morning and get ready for work. Your employer is Abyssal Depths Diving, a mid-sized engineering company that specializes in undersea cable maintenance. Your team is responsible for a Java Quarkus service that maintains the list of dive sites that the company has to go and maintain. And here's the systems architecture. There's stuff going on there. There's a few different programming languages. We have some Python, some Go, and some Java, of course. It's a bit of a mess, but it's also fairly indicative of a modern systems architecture. You turn on your fancy M4 Mac and fire up your email. And you've already got an email from John, the head of the platform team. High priority. All teams must add the platform tagging library to their services by the end of the week. And you sigh, once again tormented by one of John's various cross-cutting initiatives. But in this case, it's pretty straightforward. His team has produced a new library, the rather curiously named Horror API. The purpose of it is to be able to add a standard set of tags to the response headers from all the different services inside of your platform. Seems reasonable, and he's even wrapped it up in a nice little Maven dependency for us. We'll give him the benefit of the doubt with a snapshot. It's early days. And this is what we're trying to get going. It's pretty straightforward, right? We have our Dives API for tracking dive sites. We have the strangely named Horror API library we want to build into that. We want to run it on the JVM on top of our fancy Mac. So we get to work, we open up our text editor, and we go and add a new helper function to wrap the tags around any response from our Quarkus library. And we wrap them immediately around the get all dive sites endpoint. We fire up Quarkus dev and are immediately confronted by this rather intense looking error that you cannot possibly read anywhere in the audience. But if we scroll across really far and then squint and try and think like a programmer, we discover this bit here, which is hopefully helpful. libtag.so crazy long string is not a Mark O file. What could this be? Hi, I'm Scott. I work for Datadog. We do observability. This has nothing to do with observability, but if you're interested in that, come and talk to me about it later. This talk is about Java and how, as a high-level programming language, Java has saved us from all these terrible low-level details below the JVM, allowing us to focus on important things like building business value and writing business functions without running about how C compilers and whatnot work. But inevitably, all abstractions have cracks, right? And suddenly these cracks can open at unexpected moments and cause us all sorts of grief. This talk is about a particular set of cracks that leads down into the world of Linux and the compiler suite underneath the JVM, and how we can address those. So again, if we apply our programmer brain and go and do a bit of strategic Googling, we might ask an LLM these days, I imagine, we discover that Marco is the Mark object file format. It's used for executables, shared libraries, core dumps, and for systems based on the Mark kernel, which I can tell you with some more Googling is pretty much only macOS these days. If we go and search for SO, so the file extension we saw in that error message, we discover that it's associated with ELF, which is exactly the same thing except for Linux. So it's a different binary format used between macOS and Linux. And basically what we can see is that John, our platform engineer, has given us this jar, and it wraps up some native component, something that's not running in the JVM, and he's only included a Linux version of it, so we can't run it on our Mac. This seems a little bit overwrought for what is a fairly simple application architecture, but you can imagine that if you're in the platform team and you are John, you probably don't want to build these capabilities n times, where n is the number of all the different programming languages the programmer's into at the moment. So it's probably a reasonable strategy. And there's lots of examples of shared libraries like this outside of this little toy silly problem I've made up here today. OpenCV and TensorFlow, these are libraries that are written in C primarily, but are used by people in all programming languages. And the folks who build these aren't really going to want to go re-implement them in Java, so they're inevitably wrapping up some native code in a JNI or JNA interface and then giving you a nice way of calling into them. And this sort of thing matters more and more today, or like this class of failures matters more and more today because of things that modern deployments have led us to. Multi-architecture is pretty much the default now. If you have a fancy Mac and you deploy to x86-64, congratulations, you're multi-arch. If you deploy to AWS, they ain't going to encourage you to run on ARM because it tends to be much cheaper per cycle. So you need to be multi-arch in the other direction there. Likewise, putting everything in Docker containers is one of these things that generally just works very well, especially with Quarkus, where you get default Docker files out of the Quarkus setup, but can lead to fun impacts further on when you discover that some part of the stack that you've bundled in there has some fun native dependency and you don't know what to do with it, and it pops up at runtime. And this is really exacerbated by the use of third-party libraries that you might not even realize have some native component in them. You just chuck them in, it runs locally, and all of a sudden in production you have a fun and exciting Linux error. You have no idea what to do with it. But in this case, it should be fairly straightforward to fix. So we can see on the right, we have the different files that are in this horror API, good name, right, that John's team's built. And on the left, what we have to do, we're going to have to go and add a macOS library to it so we can work with it on our desktop environment. We're going to have to modify the Java version of the code so that it dynamically selects which library to load at runtime. And we're going to have to modify the build, which isn't going to be much fun, but is fairly straightforward for this. But first, compilers. There's really two main compiler suites these days in the land of Mac and Linux, and to a lesser extent Windows, because they've kind of gone wild and done their own thing. GCC, which is very, very old, and LLVM, which is now also pretty old, but a bit less old. And in both cases, they're made up of kind of two primary components. You have front ends for different programming languages. So you have a front end for C, you have a front end for C++, Objective-C, all sorts of other fun ones as well that aren't C related. These take individual units of source code and compile them. And then you have linkers, which take all of this compiled output, jam them together into a shared library, or jam them together into an executable given an entry point. And a fun fact of LLVM is that when it was built in the early 2000s, GCC was so entrenched in everyone's native compilation infrastructure that LLVM was built so that it can be kind of command line compatible with GCC, which isn't a small feat if you've ever used GCC. The upshot of this is kind of weird. If you go and install developer tools on your Mac and say, hey, GCC, what version are you? It tells you that it's Clang, which is actually LLVM. So it actively pretends to be the other compiler suite because it's probably going to make your life easier. So in our toy example today, we're going to end up using two completely different compiler tool chains. But for most cases, that doesn't really matter. It's just kind of a fun fact of how these things have developed. And visually, it looks like this. We take these individual units of source code, we push them one by one through the compiler, and we end up with native code built for some architecture, probably the architecture that we're running on. But we can't do much with this yet. And the reason we can't do much with these object files is because they reference symbols that exist somewhere but don't know how to resolve them. So you can imagine in this main.o, you might be calling a function in tag library.o. You have no idea where it is. You're just like, hey, go call this function, cool beans. Likewise, in main, maybe you want to print to the screen, which needs a native dependency from a C runtime library. So you end up with all these object files. They are compiled, but they're kind of useless. So you take those and you run them through the linker in a big unit, and you tell the linker what you want. Like, I would like to build a shared library, which is something that we're going to be using over in Java world. Or here's main, I want this to be an executable. And you could do both with the same object files. You could take some of it and produce a library and then add a main and say, and this is the executable if you want. If we zoom gently over to the Java side of things, it's kind of same but different. We have the Java code, we push it through the compiler, but famously Java doesn't compile native, right? It compiles to this bytecode representation, which is compiled, but kind of less compiled than the Java executable, say. But for that, we can run this Java anywhere, and we don't have to worry about these things that I'm talking about today for the most part. We then rely on a version of the Java runtime running on the particular target platform we want, which does just-in-time compilation with all sorts of fun and fancy tricks at the last minute to build it for us. The Java runtime also provides a bunch of methods to interact with native code. So you can go to the Java runtime and say, hey, I have this shared object over here. It's got this function in it. Load it up and call it. If things go well, it goes well. If things go badly, you get all sorts of exciting stack traces that are an absolute nightmare to debug. And that's what our tag library is trying to do within the Horror API. We're trying to load a shared library. So we can see on the left here, we're in the Java portion, the bit that's wrapping up our native code. And we're saying we want to load libtag.so, which is so far just our Linux native library. We need to change that so that we dynamically select one based on the operating system. If I'm on Mac, then whack a -Darwin on the end because the Mac kernel is called Darwin for some reason I can't explain. If we're on Linux, add -Linux. Then we can package both of those libraries into our jar, and we're platform independent again. We need to see how the build works to work out what we have to do to build the macOS component on Mac. So we can see from the build script, we're using Docker build. So we're building a container, and then in the second highlighted step, we're reaching into the container and pulling out libtag.so. This is a cool and fairly common pattern and means that we've containerized our build environment, so we can run this build anywhere. We can run it on a Windows machine with Docker, we can run it on our Mac, we can run it on a Linux machine as well. And the inside of it is always going to produce us a Linux binary through the magic of Docker. So what we really want to do is modify the script so we have the general Docker part at the top, and then at the bottom we have a bit that runs natively on our Mac that does the same build process there. So we jump into the Docker file, it's adding the source and the make file to Docker and then running make. We jump into the make file and it looks like a make file, which is to say full of terror. Lots and lots of symbols and all sorts of magic. And this is a short make file. I've seen some terrible, terrible things. But all we really care about here is how is it building our one source code file? How is it building our one.c file? And we come to these two bits here. The first one is a rule that says on the left of the colon, any file name .o that you need to build, you can take a file with the same name called .c, and you can run this cc step underneath with one as the input and one as the output. So that's the compilation step. This bit here is saying, now that you have all these objects, if you want to build the library, run cc again, pass all the objects in as a list, and write me out libtag.so or libtag.dylib. The last bit we need is the variables for compilation. We're asking for GCC, and we're asking to build a shared library. fpic is also to build a shared library. It makes it relocatable. If you're interested, ask me later. It's a bit of a rabbit hole. So we can take that, and we can pull it back up into our build native script, and we can throw this part under the rest of it, so it's running natively on the Mac on which we run the build. So it's essentially the same, but it's been boiled down to one command line. Run GCC, point it at the JNI include directory so it can find the Java bits it needs, point it at our source file, and ask for libtag.darwin. This should actually be called libtag.dylib because that's the convention in Mac, but it doesn't really make a difference in reality. And once we've done that, we've got this. We have two build targets, the green boxes on the outside. We have our fancy Mac, which is running on ARM. We have our Docker container, which is probably x86. Everything above the yellow line is bytecode and platform independent. Everything below is native. So in the jar, we end up having to have two different versions of the native binary, and we just pick them at runtime. So it's a bit of indirection, but we're platform independent again. So we can fire up Quarkus dev, hit that sample endpoint again, and we have our very important sample data. We have sharks, turtles, and coral at this particular dive site. So it runs. We're only 12 minutes, 47 seconds into the talk. Is it time to retire to a desert island? And then you remember, this thing runs in Docker, and because there was weird low-level stuff in here, you should probably actually make sure that the Docker build runs before pushing it into production. So you fire up Docker Compose, hit the same sample endpoint, and are confronted with another error, but in this case, a bit more opaque because we're in prod mode now. But if we jump over to the console and squint a bunch, we get something that's helpful. We can't load an AMD64 shared object on an ARch64 platform. So it's a fairly obvious hint this time. We saw at the start, we're running a Mac. Macs now, Macs like this one, are ARM64, not x86-64. And it turns out that the library that we've built in that inside bit that we haven't touched, the Linux portion of the build, is producing an x86-64 library. So if we go and look at our build script again, we can see that when we run Docker build for the native part, we're saying, I want Linux AMD64. When we go and look at the Docker file for our Quarkus application, which is wrapping the native build, actually our dive sites API, we can see in the hint about building it that we don't specify a platform. A cool trick with Docker is that if you run it without specifying a platform, it builds for what you're on. So if you go and run Docker build on a Mac, you'll get an ARM64 image if it can. If you run it on a Windows machine, you'll get x86-64. If you ask for a platform, underneath the covers, it's going and emulating that target CPU architecture as well as Docker. So when we build this image underneath and we're saying very explicitly x86-64, it's saying, yeah, okay, you're on a Mac, but I'll just build this. It'll take longer because we're emulating a different instruction set, but it'll work. And then because we're not asking for Quarkus, we're getting a native Mac app on the outside, and it's not lining up. So we have to fix it again, and it's a similar sort of pattern. Previously, we had the two operating systems that were different, that required different formats of dynamic libraries. In this case, we have different CPU architectures with them. So we need to build a Linux ARM64 image. We need to modify the jar to pick the right image again, so switch on CPU architecture as well as operating system. And when we're done, we're going to end up with 3 different variants of the same library and a bit of a Java kind of trampoline that picks the right one to use at runtime. If we wanted to be fancy, we could also do Mac x86-64 for the older Macs, but you don't see them so much anymore. And we could also do Windows, which nobody should ever use for development, I believe very strongly. So I won't. So a simple and easy way of doing this, if you're giving a talk to kind of make the point about how this can work, is by modifying the build script to parameterize out the function that builds the actual image. So here at the bottom, you can see we're saying extract native build, ARM64, AMD64. We're using some awful bash scripting to parameterize that out. We run the build essentially twice and we get 2 different libraries out of it. If you were doing this for real, you'd probably be using GitHub Workers or something like that to do your builds, and these often support parameterized Docker builds where you just have a list of architectures and it runs the thing in parallel and spits it all out the end. This is a much better idea than what I've done here, but this is at least a little bit illustrative, hopefully. And once we've done that, things look a bit like this. We have our 2 targets still, but the Docker container has to run on AMD64 and Arch64. And we have 3 different variants of the library that we are then dynamically selecting at runtime. We could also be really jazzy with our outside Docker container and make it so it could run the parsers API, the dive-side API itself could run on both ARM64 and x86-64, and then it would be very, very portable. So we fire up Docker Compose again with our development image, we hit the URL, and it works, and we still have the same sample data, which is very unsurprising. But it's not quite time to retire yet. You remember that you also have an Alpine Linux image for production because you like small, efficient production images, and you're using a Ubuntu base image so far for Quarkus otherwise. So you go back to your Docker Compose environment, you change it again to use the Alpine production image. Does anyone think it will work? Out of curiosity, is this going to be the end of the talk where everything's successful? I see no hands. This is good. And again, it's broken. The error ID is exactly the same, but this is a coincidence and not because I reused the same screenshot. So if we jump back to the console this time, the error is a little bit more opaque. Error loading shared library LD Linux ARch64. No such file or directory. And we can see that it's needed by our libtag Linux ARM64, so this shared library that we've been working on. But this probably doesn't help most people, I would say, with what's happening. But we have a vague suspicion that something funny is going on with our native library because we never had these errors just running on Java, right? And on Linux, you have this tool called object dump. You can point it at binaries or shared libraries or anything that's an ELF file, essentially, and ask for stuff in it. So here in the first command, we're going into our Alpine container and saying, hey, object dump, the Java runtime, what shared libraries does it depend on? And objdump's telling us it depends on libgil and libcmusl ARch64, which is suspiciously similar to the error message we saw before. If we ask it the same thing about libtag Linux AMD64, it tells us that it has a dependency on libc.so.6. So these both sound the same, but they're subtly different. And if you grab the musl one and copy it over to the other one, which isn't in the Alpine Linux image, this will not work. An aside, C runtime libraries. When you want to do something on a computer that affects anything in the outside world, you have to ask the kernel to do that for you. That means opening sockets, connecting to a server, writing to a file, printing to the screen. All of these are delegating to the kernel. And the way that kernel calls work, in Linux at least, is you put a bunch of magic numbers into a CPU register, like maybe if you write 12 to EAX and put a string buffer in EBX, it means print to the screen. I have no idea. And then you fire a soft interrupt, which kicks the CPU into kernel mode, which then reads the magic numbers out and decides what you want to do. This is not very ergonomic if you're a programmer. So we have C runtime libraries to do this. These are things like glibc. There's a bunch of different variants. glibc, musl that we've just seen. These are the 2 main Linux ones. MSV CRT for Windows, if you've made the terrible mistake of using Windows, and probably heaps of other ones that I have never heard of. And they're just ordinary shared libraries. Like our libtag library is a shared library. It's a binary that we can load in other applications and call functions in at runtime. glibc and musl are the same. They expose functions like printf and opensocket and whatnot. But they are distribution specific. So when you use most Linux distributions, you end up with a dependency on glibc. This is the old and established one. But Alpine famously uses musl because Alpine tries to be a small, focused, very fast to start Linux distribution. And musl is much smaller than glibc. And when you build something on top of Linux, pretty much anything, you end up with a dependency taken on that library or that application on the C runtime that was visible. So in the top screenshot here, when we build our shared library on Ubuntu, we end up with a dependency on glibc. We haven't asked for it, but it's there. So to support Alpine at runtime, we have another variant. We have operating system CPU architecture and now C runtime library. But it's pretty simple in this case. We can basically just take our Docker file, copy it exactly as it is, and just swap these first two lines. So we use Alpine as a base image, and we use Alpine's package manager to install our compilation suite. Everything else works exactly the same, but the shared library that shakes out at the bottom is dependent on musl and not glibc. And when we've done that, we have a lot more going on. We have variants by CPU architecture, operating system C runtime library. We can run all over the place, but we've jammed a whole lot more into the library. And this also gives you a bit of an impression of how much misery Java is saving you from, basically. And also how much misery well-built native libraries in Java save you from, without you even realizing it in some cases. If we crack open OpenCV, for instance, the jar for OpenCV, we can see that it's doing exactly this. It's full of native code for every combination of platform and CPU architecture, and it goes on with the runtimes as well. And you really don't realize this unless you go and decide to run a Java application that uses OpenCV on a CPU architecture or a platform that Java supports, but OpenCV doesn't. And then you will end up with this exact class of errors. But anyway, we've done all of our indirection with the builds. We can fire up Docker Compose again with Alpine. And we get our very important and very static sample data once more. You've not had a great time, but you've probably learned a little bit about C runtimes, at least how they pertain to Java. You pat yourself on the back, push your commits, and they were rapidly released to production. And that's all I've got. Thank you for listening. I hope that was interesting. I have 2 minutes and 40 seconds if anyone has any questions. No questions, so I assume that was all very clear and well presented.
Is there a background to this, an anecdote that caused this horror in your own experience?
It's a thing that I've explained over and over and over again to people who end up in this situation by adding seemingly innocuous dependencies to their Java builds. And I've explained it enough times that I thought I would tease it out into a hopefully moderately entertaining talk and save explaining it again.
Makes sense. Thank you.
No, it's... Cool. Thank you for your time. Enjoy the rest of the talks.